Hello everyone. Today, inshallah, we will continue our journey with functions, with the differentiability of functions. This is the lectures 13 and 14 covering the work of this week. Earlier, I believe I sent you the PDF for this lecture, also the PDFs from Lesson. All our course notes, references, you will find them on Moodle, and also the recorded sessions, all of them you will find them on my YouTube as usual. I want to confirm that this PDF covers both the main slides that was sent from Lisbon and also the part covering this particular topic, which is 3.2 in the mathematical analysis book that you already have, plus some problems from the previous exams. So it's supposed to cover this area completely. I've sent you, as I told you, the PDF for this lecture 2 days ago. I believe on Friday. I sent it on Friday or something like this. Tomorrow I will continue. If I finish today our lecture, then you are free tomorrow. If you have questions or anything, I will be here in the campus, so you can stop by and ask me anything that you need. Okay, let's start. As I told you, today we are going to differential calculus, but we are going to cover 3.2 and 3.1. So the agenda of today is to continue differentiability and differential functions, equation of tangent plane, the directional derivative, and this is the topics that we are going to cover today, also with the differential as I told you. So differentiability and differential, plus the equation of tangent plane, plus the directional derivatives, and also if we need to approximate the value of a function near a certain point using the differentiability equation, we can do that, as you would see. So this is why I'm telling you this is really a very important lecture to be added to the previous ones, inshallah. So mainly, I want you to remember that the total derivative is the rate of change of the output function or of the output of a function relative to the change in the input. Although we did go through this previously, but I would like to take it as an introduction for what's going to happen in R2. Of course, we are here working on this example is from R into R, or covering the idea of functions in one variable. But we will use this also, or this is this entrance or this introduction to go through the R2 or Rn in general, as you will see. As I told you previously, if I want to find the derivative, the main formula is or the derivative can be divided at the slope of tangent, as you know, or the rate of change of the output relative to the input. So if I'm looking to the output, it's going to be f of x minus f of a divided by x minus a, which is the derivative law that we already know. Why? Especially when x is trying to approach a. So this is mainly the limit that we are seeking to solve. If you look closely to this limit, which is the limit when h tends to 0, f of a plus h minus f of a over h, and that's the limit of the derivative that we used to have. If I combined these two parts, okay, f of x minus f of a divided by x minus a with f dash a, I will be able, since the derivative exists, if the derivative exists, then I will be able to state that f dash a, okay, times x minus a equal to f of x minus f of a, and that's the equation that I will depend on in knowing or studying the differentiability, as you will see from the coming slide. So if I want to get f of x, simply f of x will equal to the value of f at a plus f dash a times x minus a, plus a remainder term which is supposed to tends to 0, as you will see from the coming slides. So while we are here, remark that the slope of the line of the tangent line at point A, we can get this slope from this relation, and as long as x tending to a, this approximation or this value will decay while x approaching a. This is mainly, as I told you, the idea that I will depend on the coming slides, as you will see. So mainly, this is the introduction from the definition in R to R. If we are talking about the differentiability in general, the function f R is differentiable at a point A if in A, neighborhood of A and f of A. We may write approximate the value of f. As I told you, this is exactly taken from the previous slide, which is f of x equal f of A plus the derivative of the function at a times x minus a plus the remainder term. So if the function is differentiable, the value of or the remainder term will tend to 0 while x is approaching a. So the limit of the r of the remainder term while x tends to a will be equal to 0, which means that the remainder will approach 0 further than h approaching a, and so this is the approximation error, as I told you. And it's all coming from the previous slide, as I tried to say, as I tried to outline in the previous session. Also, the equation of the tangent line to the graph at a and f of a will be taken from this equation. So actually, this slide summarizes everything. As I told you, still in the case of from R into R. So mainly, if your function is differentiable, you will be able to find the equation of the tangent using this equation. Also, you will be able to approximate the value of a function in the neighborhood of point A using this equation. Plus, I can test any function, if it is differentiable or not, by simply trying to test the remainder term if it goes to 0 or not. The coming slides will contain plenty of problems just discussing this issue, okay? Getting the value of R. And before we go further, I will stress on this further also, but at the time being, also remark that R of x minus a, it's really simple to have. Because I can say that R of x minus a equal to, if I moved those two parts to the other side, so the remainder term will be f of x, this is minus f at a minus f dash a times x minus a, and that's the equation of the remainder that I will depend on in order to make my analysis or to test if the remainder term is going to 0 or not. This is how to evaluate the value of the remainder term, as we will see from the coming slides, inshallah. Okay, this is the definition. This is the tangent line or the approximating equation that we will see down the road. So once more, the function is differentiable at a if and only if. F dash a is finite, which means it's a value you can have, means derivative exists and is defined. Also, the proposition is really very important. If f is differentiable at a, then f is continuous at a. But the converse of this statement is not true. So once more, if f is differentiable, then f is continuous at this point, and this applies in R or for functions mapping elements from R into R. Once we go to discussing the relation in R2, okay, the search will be a little bit different. So, first of all, remember that f, it's line from R into R. If the function is differentiable, it is continuous. That's the statement of the previous theory. And if the derivative exists, it is differentiable at any point within the domain. Okay? But in two dimension, remark, this is very, very important. For functions from R into R, or functions in several variables, remark the difference. A function with two variables and at point A, which belongs to the domain of the definition of this function, the existence of partial derivatives of f at the point is not sufficient to guarantee the differentiability of f at this point. So we previously knew that the first derivative for several functions in several variables will be partial derivatives, because you will have to assign or to determine what's the derivative of your function and with respect to which variable from the variables, from the input variables. But in these functions of several variables, the existence of partial derivatives doesn't guarantee the differentiability of this point, and you will see an example on this shortly, inshallah. The concept of differentiability of f in AB is related to the existence of non-vertical tangent plane, which is called Z, which is mainly a generalization to the previous idea. So once more, the main idea in the two dimension, it is in one dimension we find a tangent plane to your curve. So once more, if this is the y-axis and that's the x-axis, and this your function, and that's the tangent plane, or I'm sorry, the tangent line that we are seeking to find at certain point. If we move to other dimension or two dimension, the step as a simplification to functions in several variables, the first of them is for R2 into R, and in this case, instead of having a straight line as a tangent, we will have a plane as a tangent for your function. But still, the main equation is the same. So, for a function f of x and y, it's equal to f at a and b. In this case, that's the first derivative times x minus a, or times the vector, plus a remainder term, as you will see in the coming slide directly. As you remark, I'm talking about this slide and also explaining the coming slides because the ideas is really connected to each other. So just wait with me. At the time being, I want you to focus that if I want to find a tangent plane at a certain point, this is going to be the equation that I'm going to use, which simply states that the plane which is tangent to a curve from R2 into R, or the function from R2 into R, it's going to be simply the value of the function at a and b, then get the partial derivatives if exist at x or y, then substitute by a and b in both those partial fractions, partial derivatives, then multiply in x minus a, y minus b, then you will have your tangent plane, as you will see shortly, inshallah. That's the definition. As I told you, there is two, if I'm discussing the differentiability of functions in R2, there is two main points I will have to discuss. The first of them, the existence of partial derivatives. If the function which we are studying its differentiability at certain point doesn't have partial derivatives, or its partial derivatives doesn't exist, so it's not differentiable. This is number one. Number two, f can be approximated at point xy, which is close to AB. That's the equation of approximation, which is exactly, if you remark, the main equation in R1, or from R into R, as you will see in the coming slide. This is the value of the function. That's the value of the function times partial f partial x, x minus a, which is the value of the tangent plane, and that's the error term. If your function is differentiable, then the error term will equal to 0, which means the limit of the error divided by the norm is going to be equal to 0. And that's once more stating that the error term will grow smaller, faster than x, y, approaching a and b. And so the error term will disappear, and this is going to be the equation that I will use in order to approximate all the tangent plane at this point. So once more, as I told you, exactly. And that's the tangent plane. Once more, that's the curve that we are talking about. So once you are moving from any side, x and y, approaching the point A and B, as you can see, the both points are equal to each other. It's a tangent point. So the point belongs to both the plane and your curve. And so the error will equal to 0, or this value is going to be 0. So I can use them to approximate. if you make the substitution in order to get the error, it's really very simple. And exactly like what I explained in the previous lecture. In the previous slide. I will take this part and move it to the other side. So actually I can change the value of the error term by f x and y minus f of ab minus these two parts, as you can see. So actually it's really very simple. This is mainly how to check if your function is differentiable or not. This question is really very important, which states that if f has finite partial derivatives at a, then f is differentiable at point A? Actually, no. Unfortunately, no. The answer is no. So I may have functions having partial derivatives, but still not differentiable at this point or at the point that we are discussing. Once more, this is the approximating equation, or that's the differentiability condition for function from R into R. If we are talking about, this is from R to R, once more, this is from R to R, okay? This is from R to R, a function is mapping, and this equation for f running from R2 into R, and for Rn, it will be a generalization for this function. So once more, the f of xy will equal to f at a and b, plus the gradient vector at a and b, dot product, okay, with x minus a, y minus b, as you can see, plus the remainder term, which we will find according to the definition that we stated previously. So mainly, that's the function, your function, if you want to test it. It has to have partial derivatives, because I'm going to use them, and also the limit for the remainder term should equal to 0, as we will see. The equation of the tangent plane, it's this part from the equation. This is the part of, instead of having f of xy, this is going to be z equal to f a and b, which is plus f dash of x, the partial derivative of f with respect to x times x minus a, plus the partial derivative of f with respect to y times y minus b, as you can see. So that's the equation, as I told you, of the tangent plane to a certain curve in R2. This is the main equation that we will use. So I believe at the time being, before going to problems, I want to stress on these facts. F is differentiable at AB. This is going to lead to that f has both finite partial derivatives at AB. So it is a condition for this. If f is differentiable, those are consequences for differentiability at AB, then f is continuous. So my game, if I want to see that f having both partial derivatives or finite derivatives, then try to prove the function is differentiable. So if it is differentiable, then those two guys already exist. If it is differentiable, also f is continuous. But remark, the existence of finite partial derivative doesn't guarantee that your function is differentiable. So once more, it is a necessary condition for the function to be differentiable at that point, but it is not a sufficient condition for the function to be differentiable at the stated point. So once more, that's the main equation, the main test for the differentiability. I will write this one. I will try to get the value of r, which is the limit of xy tends to ab, and testing that this limit exists and it's equal to 0. Of course, we studied the limits previously, so I will have to study this limit as we did previously, going through the directed method, the iterated method, or using Cauchy definition for finding a limit for such this function, or using the corollary of the squeeze theory, if you remember, in order to solve this problem, as we will see shortly in the coming slides. To prove that a function is differentiable in R2, as I told you, step number 1, find the partial derivatives. Be sure that these two guys really exist. Step number 2, try, as I told you, if they don't exist, then your function is not differentiable. Second step, find the expression of R, which is really very simple. F of xy minus the value of the function, minus the gradient vector times x minus a and y minus b, as you will see. Finally, check if the limit is equal to 0. If the limit doesn't go to 0 or it has a value different than 0, then your function is not differentiable at this point. And of course, if the limit doesn't exist, then also the function doesn't exist. So once more, if the limit doesn't exist or doesn't approach 0, if it is exist or not equal to 0, then your function is not differentiable. I'm talking about the evaluation of this limit. We are in very deep need, or we are in deep need to have an example on this. Let's see this problem. You want you to check using definition. So I'm here asking you to use the definition of the differentiability, where the following function is differentiable at the origin or not. The function is a piecewise function defined by x squared plus y squared, while y doesn't equal to 0. But if y is equal to 0, the value of the function is equal to 0. Okay, I will start by finding the partial derivatives of this function. Since it is a piecewise function, then I will try to get the partial derivatives using the definition. Yes, you're right. I can get partial f partial x, as you will see, by discussing the limit of h tends to 0 for the function of h and 0 minus the value of the function at 0 and 0 by h. And in a similar manner, I can also discuss the existence of partial derivative of y with respect of f with respect to y by considering limit k tends to 0 for the function of 0 and the k minus f 0 and 0 divided by k, and see if these limits exist or not, as you will see from our solution shortly. So all I have to do at the time being is try to use these laws in order to find the partial derivative. Why not to differentiate directly in order to get your partial derivative? Because it's a piecewise function, as you can see. So once more, the partial of f partial x, it's the limit of h tends to 0 of f 0 plus h at 0 minus the value of the function. I want you to remark that I'm studying the differentiability at the origin. So this means I will have to get the value of the function at the origin, and this is really very simple. The piecewise function solved this issue because the value of the function at the origin when y is equal to 0 is equal to 0. So this part is equal to 0. So I'm talking about this part here in particular, which is f at the input 0 and the h and 0. If you make these two quantities and start substituting in the general function, you will find that it is h squared plus 0. So once you start substituting, as I told you, so it's gonna be 0, okay, plus h to the power of 2, plus 0, which is h squared, minus f double 0. So the denominator is h squared divided by h, which is gonna be an h taking limit h tends to 0. So it exists and it's equal to 0. In a similar manner, as I told you, as explained, as a similar manner for studying the partial derivative of f at the origin, it will be exactly the same. 0 for the x component, 0 plus h for the y component. Taking h equal to 0, this guy is equal to 0. This is gonna be h squared, because this is gonna be 0 to the power of 2. And this is 0 plus h to the power of 2, which is h squared. So h squared minus 0 over h, it is gonna be h, while limit taking to 0, so it's gonna be 0. So bottom line now, the first condition is satisfied, that both partial derivatives already exist and both of them equal to 0. The second step, I will need to get the remainder term. Do you remember the remainder term? I will write it with you, then I will erase it and you will see it on the slide. Once more, r of x minus 0 and y minus 0 is going to equal to the value of the function at the origin, then plus get f sub x times x minus 0 plus f sub y times y minus 0, and once more, this is simply is the gradient of f at the origin dot product x minus 0 and y minus 0. This is exactly what you can see, and this is explicit 4. Of course, since we are getting r, these two signs are negative signs, or simply it is the negative of the gradient effect. So this is what we are going to see at the time being for trying to get a definition for the remainder term. So once more, it's very, very simple. Once more, as you can see, this is f of xy, which is going to be 0 and 0, partial f partial x times x, plus partial f partial y times y, and that's the remainder term. This is 0 because the existence of the partial derivative, which is equal to 0. That's 0 also, and the value of the function is equal to 0, which leads to that the value of the remainder equal to the value of the function. So now I need to evaluate the limit. That's the second step, to find r, which is equal to f of xy. Third step, if you remember, just to trying to solve this limit, which is very, very simple. It means that I will have limit of x and y tends to the origin, and then replace r by the f of x and y divided by the norm of x and y, which is simply the root of x squared plus y squared, which will lead to limit x and y tends to the origin. If you use the substitution of the function, which is simply, it's gonna be x squared plus y squared divided by the root of x squared plus y squared. If you eliminate this guy with that one, you will have the limit of x and y approaching 0 and 0 for the root of x squared plus y squared, which leads to then the limit existence equal to 0. Now I have the partial derivatives exist. The check for the remainder term already applicable once we start substituting, and also is equal to 0, which means that the remainder term decays and equal to 0. That's this function is differentiable at the origin. All I did is just steps and direct substitution in the equation, as you will see, in the limit. So once more, this is gonna be r of xy by the norm of xy. I want to check if it's equal to 0 or not. All I have to do is to replace r of xy by the value of the function, which is x squared plus y squared. This is actually x squared plus y squared. It is the square root to the power of 2, and that's the square root of x squared plus y squared. Cancelling them together will leave you with this guy, which is equal to 0, which means that f is differentiable, as I told you, and we tried to solve it together. Once more, that's another problem with the same direction and the same check. I want to check if the function is differentiable or not, but remark that you have x times y is greater than or equal to 0, which means this is the first and third quartiles, while if your value or the values of the function belongs to the second or the fourth quartile, I want you to take care of this issue or to remark this relation. If I told you x, y is greater than 0, so I'm talking about q1 and q3. But if I told you xy is less than 0, then this is the case of x, y less than 0. In this case, I'm talking about the fourth quartile and the second quartile. So if your x times y or xy belongs to greater than or equal to 0, I will use the root of xy, otherwise it will be 0. I want to check the differentiability of this function, and of course at the main point, which is the origin. So all I have to do is to get the partial derivatives once more. Since my function is defined on more than one domain, so I will use the definition. That's the partial derivative of f at the origin in the direction of x, which is going to be 0 plus h and 0. If you try to substitute by these values in the root of x and y, it's going to be 0 times 0 plus h, which is 0. So the function is 0. And minus f0 and 0, the same definition, which is going to be 0. So the denominator is equal to 0, which means your partial derivative exists and the value is equal to 0, while that's the value of the partial derivative with respect to x at the origin. Similar manner, if I'm getting the value of the derivative of the function with respect to y at the origin. It will be a similar debate, but instead of having the x 0 and h, the y will be the part with 0 and h. Also substituting will lead to it's equal to 0. So now I have the partial derivatives exist, and the both of them equal to 0. I will move to the second step. The second step is to get the remainder term. The remainder term will be got from the equation of the function, where if at 0 and 0, in this case I will use the upper part, which is equal to 0. So this part decay. The derivative, partial derivative already exists and equal to 0. The partial derivative at y is equal to 0. So all of this gonna vanish, and you will have f of xy equal the remainder term exactly like the previous problem. So once more, it is required from me to solve the limit of root of xy divided by the root of x and y. If I want to solve this equation or to solve this problem, it's very, very simple. All I have to do is to get the limit of x and y approaching the origin, as we see from this substitution that r is the value of the function. So it's going to be a root of x, y divided by the root of x squared plus y squared. I will use the iterated this one. If the value of this limit doesn't exist or doesn't equal to 0, then it's not going to be differential. So I suggest, boom, boom, okay, I will take y to test at y equal to x. If I'm using y equal to x, it's going to be the root of x squared, and it's going to be divided by 2 of an x squared, and that's the limit of x and y approaching 0. So in this case, remark that the limit will exist and there will be 1 over root 2, which doesn't equal to 0, which means your function is not differentiable. So this function not differentiable at the origin. This example is really very important, because as you can see, although I have the partial derivatives, they are exist, and the both of them is equal to 0, your function is not differentiable at the origin. So once more, if I'm trying to do this once more, all I have to do is to start substituting as I told you. So I will replace r of xy by the root of x and y. I'm using y equal to x, so it will lead to the root of x squared by the root of 2 of x squared, eliminating x squared from the denominator and the denominator. The limit does exist, was not equal to 0, so once more your function is not differentiable at the origin. So that's the second example. For this problem, he wants you for each of the following parts state and justify whether the function at the indicated point general expression is differentiable at A. If so, use the derivative to estimate the value of the function at f of B. And for this problem in specific, he wants you to test x over y at the point 1 and 1. And if it is differentiable, try to approximate and find the values at 1.1 and 0.9. It's really very simple. All I have to do is to stick to the plan. 3 steps. 1, 2, 3. The first step is to try to find the partial derivatives of f at the stated at the point that we are dealing with. I have x over y. So for this function, it's not given as a piecewise function, and I can find the first derivatives, which is really very simple task to do at the time being. So if I want to find partial f, partial x, or simply f of x, all I have to do is to differentiate this guy. So x will be differentiated, it's going to be 1 over 1. And if I want to get partial f, partial y, it's going to equal to f sub y, which simply I will differentiate x, y to the power of negative 1. That's going to be negative x times y to the power of negative 2, which is simply negative x over y squared, as you would see. Those are the partial derivatives of this function. So once more, this is f sub x, it's going to be 1 over y. And for f differentiated with respect to y, This is going to be y to the power of negative 1. The derivative will be negative x over y squared. If I want to evaluate these values at the point of study, or at this point in specific, which is 1 on 1, all I have to do is to substitute. Simply, so I will substitute in this function, which is going to equal to 1. Then I will substitute in the derivative of the function with respect to x, which is going to be 1. And also I will substitute when we are differentiating the function with respect to y, which is going to be negative 1 over 1, which is simply negative 1. So I have the value of the function, the first derivative with respect to x, the first derivative with respect to y, as you can see. The second is to find an expression for the remainder term. This is the general equation that we use for approximation. So all I have to do is to get r of x minus 1, I will call it h, y minus 1, it's k, and we will have 1 plus h, 1 plus k, minus f at 1 on 1, minus the gradient vector of the function at the 1 on 1 times h and k, which is x, as we will see, x plus a and y plus b as tilde. So all I have to do is to make the substitution. That's the value of the function, as I told you, at h plus 1, 1 plus k, minus the value of the function at 1 and 1. Then I will multiply the first derivative, which already I have, times h plus f of y times k. Where h and k, as I told you, it is x minus 1, y, h is equal to x minus 1, and for k it is y minus 1, which are the neighborhoods of the points that we are dealing with. In this case, h and k will approach 0, and all I have to do is to try to find the value of this function. So I will start substituting using the definition that's x is equal to h plus 1 and y equal to k plus 1. If I take this substitution and substitute in x and y, this is going to be from here, it's going to be h plus 1, divided from there, it's going to y equal to k plus 1. This is why you will see the value of the function at 1 plus h and 1 plus k is going to be 1 plus h over 1 plus k. Already the value of the function at 1, very simple. I will replace those guys by 1, which is equal